Hello guys, so today our topic is planar graph. This is a very important topic, every year from this topic there are lots of questions in gates, UGC net and many competitive exams. So this is very important, and I will suggest you to work, just see this topic very sincerely, because every times some little bit easy questions come from this topic. But if you don't take it seriously, then you cannot get the easy marks. Okay, so from this topic the getting marks is very easy. So let's begin. So before starting, what is planar graph? So we need to know some basic things. So first of all, we need to know what is crossover. Whenever two edges are drawn with a overlap between them, then that is called crossover, like that. So let's say this is one edge E1 and this is another edge E2. Okay, so you can see there is a overlapping between E1 and E2 over here. So this is a crossover, we can say. And when we draw this same thing without a crossover, let's see how we can do that. So we can take E1 as it is, like that, and we'll take this vertex and we'll draw the E2 like this. Okay, so it have the same properties that this graph have, but this graph doesn't contain any crossover, but this contain a crossover. So we can remove the crossover like this by drawing the graph differently. Okay, so first of all we need to know one basic fundamental thing, that is what do you mean by planar representation. Okay, so planar representation means drawing a graph without crossover. Means we have to draw the graph without having any crossovers, like that we have discussed. Let's say this is the graph G, this is our graph G, and we are just drawing the graph differently, and this is the planar representation of the same graph G. It means that this is also graph G, this is also graph G, but this having a crossover, and this representation doesn't have any crossover. So we can say this is the planar representation of the graph G. Now we know the definition of the planar graph. So this is our main topic. So let's see the definition. At first, this is a very easy definition, that a graph having a planar representation. Whenever any graph having a planar representation, or we can draw the same graph without any crossover, then that graph is called planar graph. Let's see some example and let us decide if the graph is planar or not. So I'll suggest just see the examples and stop the video and try yourself, and then match with me. Okay, let's see from the example 1. So this is the example 1. So you can see these are the 4 vertex, 1 2 3 4, and these are the 6 edges, and you can see there is a crossover over here. So this is not a planar representation, but we cannot say that is the graph is planar or not. So let's see if we can draw this graph without any crossover or not. So let's see what is the planar representation of this. Let's see. So we can draw the structure like this, and let's suppose this edge is like that is has. So we can draw this edge like this. So this will not harm any properties of the graph, but we can draw the graph differently. So this is the planar representation of the graph G. So we can say this is a planar graph. So this graph is a planar graph. So I'm just ticking. Okay. So in the example 2, this is very easy, and this is already the planar representation, and this graph doesn't contain any crossover. And if a graph doesn't contain any crossover, so by default that graph is planar graph. So this is a planar graph. Okay, fine. Let's see. Just try this one, and I'll just pause this video, and after that you can match with me. Okay, so you can see there is 2 crossover. One is here and another one is here. Let's try to remove the crossover. Okay, so I'm just drawing the edges like this, and for this edge I can draw it like this. Okay, so this is the planar representation of this graph. So we can say it like this is the planar graph. Okay, let's see. So for this graph, if we try to draw this graph without crossover, we cannot draw that. Let's do it. Why will you believe my words? Let's do it. Okay, I'm just I'm just putting the vertices. Now for this vertex there is 3 edges, just draw like this. Okay, for this vertex, let's suppose we have to draw this without any crossover, so we can do like this. For this edge we can draw this edge like this. Okay, and for this edge we can draw like this only. Okay, there is no problem. Now for this edge we can draw like this. Now for this edge, let's try to draw it, but we can draw it like this only. Okay, there will be no crossover. But for drawing this edge, we cannot draw it because there is no path exist, because if we try to draw it, there will be at least one crossover. Okay, if we want to go from here to here, we have to make some crossover like this. If we draw this, there will be crossover, so we cannot draw the planar representation for this graph. So this is not a planar graph. Okay, for this graph, let's suppose if we can draw the planar representation or not. So first of all, do the boundary part and let's try to draw without any crossovers. So this much is enough. Now for this edge we can do like this. For this edge we can draw like this, but for this edge there is no path from where we can draw this edge without any crossover. So for this also we cannot draw the planar representation, so this is not a planar graph. Now let's see the example number 6. Is this graph is a planar graph or not? So by seeing this we can say that this is not a planar graph, but that is not true. This is a planar graph. Let's see how it is true. Okay, so we can draw this graph like this. This is the background parallelogram, and this parallelogram we can shrink that parallelogram and put that into the big parallelogram. Okay, and do the next connections like that. Okay, so this graph and this graph is same. You can verify it at your home, and these two will be equal, so we can say this is a planar graph. So we have done lots of examples. Now let's see some definition. So what do you mean by region? Okay, so this is an important term. What do you mean by region? So the planar representation of graph divide the whole graph or the whole plane into some region or some small part, that is called as the region, or we can say it like the face. So first of all, see how many region this graph has. So this is the planar representation of the above graph G. Let us assume, let us see what are the regions this graph have. Okay, so this is a closing part, so we can say this is the region A. This is another closing part, we can call it region B. This is another closing part, this is also, we can say it like C, and the outer region is also a region, so we can say the number of region is 4. So R is, we can say like 4. Region is represented as the capital R or smaller, whatever you can. Yeah. Okay, so for this graph, let us see how many regions it has. So this is one closing region, so this is A, and the outer part is already a region, so this is B. So number of region is 2. Let's see how many regions this graph has. So this is one closing region A, this is another closing region B, this is another closing region C, this is another closing region D, and the outer part is a region, so this is E. So this is not a planar graph, so we cannot find the number of regions. This is also not a planar graph, we cannot find the number of regions. Let us suppose how many regions this has. So this is A, this is B, C, D, E, and the outer region F. So R is like 1, 2, 3, 4, 5, and 6. So how many regions this has? This has 5 regions. This is 5 regions. Okay, fine. Next. There is a note that says number of edges in the boundary of the region is called as a degree of region. So number of edges in the boundary of any region is also called as the degree of region. Let's suppose what is the degree of region of A. So how many edges it have in the boundary? So this is having 1 2 3, so 3 edges. So the degree of region A is 3. What is the degree of region B? So this is also having 3 edges, 1 2 3. So degree of region B is 3. And degree of region C, let us suppose how many edges it has in the boundary, that is 1 2 3. So this is also the number of edges in the region, degree of the region C is 3. Now what is the degree of region D? Let's say this is the one is this is 1, this is 2, this is 3. So we can say all the regions have the same degree in this case. Okay, so we are not considering this edge and this edge. Why? Because we have already defined that boundary, the number of edges in the boundary of the region, not the internal edges we have to consider. Okay, so how many what is the degree of region A? So you can say like this, there are 4 edges it have in the region part. So degree of region of A is 4. So we can also see that the degree of region B is also 4. You can validate for all the graphs, and you can send the answer in the comment box. Okay, so this is the thing. Now there is a formula that is called Euler's formula. So Euler's formula says that V minus E plus R is equal to 2. Okay, so this is the formula, you have to remember this. So what is the V? V is the number of vertex in the graph, and what is E? E is the number of edges in the graph, and what is R? R is the number of region in the graph. Now we have to validate these things for our graphs. Let us suppose the first vertex. Okay, so what is the number of vertex? You can see like 1 2 3 4. So number of vertex is 4. What is the value of E? That is number of edges. It has 6 edges. You can see 1 2 3 4 5 6. And how many regions it has? We have considered that is 4. Now the formula says that V minus E plus R is equal to 2. So there is V means 4 minus E, that is 6, plus R, that is 4. So what does this gives? Like 6, 4 minus 6, that is minus 2. Minus 2 plus 4 gives 2. So the formula satisfies here. We can validate for this also. So what is the value of V? That is 4. What is the value of E? That is also 4. And what is the value of R? That is we have found that is 2. So V minus E plus R, how much is this? Is like V is 4 minus E is also 4, and the number of region is 2. So 4 cancel, and this gives a 2. So here also the formula satisfies. You can validate for every planar graph in the universe. So the formula satisfies. So this formula is known as Euler's formula. So there are many questions regarding this formula. If you can remember this formula, you can solve the questions. So there are many easy questions available in the previous year questions of GATE and UGC NET. You can solve the questions. So there is important result we have, that is summation of degree of region, that is equal to less than equal to 2 into number of edges. Okay, so this is one formula you can remember. And if the graph doesn't contain any internal edges, then we can say like that degree of region equal to 2 into number of edges. Okay, so what does the internal edge means? If this graph having one internal edge like this, okay, so then we can say it like this is the internal edge. because this edge doesn't give any significance for the edge, for the region calculation. So this is called as the internal edge. Okay, so for this case we can for this graph we can validate this formula. Let us draw this graph here again. So this is our graph. Okay, so it has two regions, that is A and that is B. Okay, so degree of A. Okay, so d of A means degree of A. So what is the degree of A means what is the number of edges in the boundary part, that is 4. And what is the degree of regions in the outer part for B, that is also 4. Now degree of A plus degree of B, what is how much, that is 8. Okay, and what is the total number of edges it has, like 1 2 3 4 5. So E is 5, so 8 will be always less than equal to 2 into 5. So this means 8 is less than equal to 10. So this is satisfied. If it doesn't contain any internal edge, let us see the example. So like this. So this graph doesn't contain any internal edges. So this has two regions A and B. So degree of A is 4 and degree of B is also 4, and number of edges is also 4. So degree of A 4 plus degree of B 4. This is always equal to 2 into number of edges. So 8 is equal to 8. So we prove the theorem. Okay. So this is the simple proof of the result. Okay. Let's see the remaining part. Now there is two special graph in our case, that one is Kuratowski's graph. So Kuratowski's have two special graphs, that is K5 and K33. These two graphs are non-planar graph. Okay, so K5 and K33 are non-planar graph. Okay, now we need to define some operations. The operation name is called as the homeomorphic operations. So these contain two sub operations, that is adding a vertex in a series and merging edges in a series. So adding a vertex in the series means, let us suppose there is a edge like V1 and V2 are two vertices and E is the edge. So in this series we can add one vertex like V1, V3, V2. Okay, so we add the vertex in between V1 and V2. So this is called as the homeomorphic operations. Okay, this is called a homeomorphic operation, and we can like this also we can remove any, or we can merge the edges. Like let's say these are the two edges and V1, V2, V3, this is the vertex. We can omit the V2 and or we can merge E1 and E2 and make them one edge, and the V1 and V2 and V3, and we can omit V2. So these two are called homeomorphic operations. Now there is a important theorem in this chapter, that is called Kuratowski's theorem. So it says that a graph G is planar. So this symbol satisfies if and only if, or biconditional. So I am just giving in the symbolic format. So G is planar if and only if it doesn't contain any subgraph that is homeomorphic to K5 or K33. So detection of planar graph is very difficult for the computer algorithm purpose, but from the theorem says that if it contains any subgraph that is homeomorphic to K5 or K33, we can directly say that graph is not a planar graph. Let's see some example. Okay, let's draw some arbitrary graph. Okay, so we cannot draw everything and everything that and see if the graph is planar or not non-planar. So let us suppose there are many subgraphs. Let's see this subgraph. Okay, is it K5 or K33? No. Okay, so we can say, and this graph is already this subgraph is already a planar, and for this subgraph this is not homeomorphic to K5 or K33. So we can say like this blindly that G is planar graph. Okay, let's say another example. Okay, sorry for that. So let's see this is planar or not. Okay, so we can see directly that this is not K5. This is similar to K5, but this is not K5. But in this region, you can see in this region, so there is extra vertex. So using the homeomorphic operation, we can omit the vertex using the operation 2, or merging these two edges into the same. So we can rewrite the graph like this. Okay, and you can see this is K5. So this graph is homomorphic to K5. So we can say this graph G is not a planar graph. Okay, simple. So if any graph contains homeomorphic to K5 or K33 or any component like that, so this is not a planar graph. So this is the Kuratowski's theorem. So thank you very much for watching, and this is all. Thank you.